Now, we are going to discuss the most important topic of this chapter, which is rotation with constant acceleration. In the preceding section, we have to define the rotation variables. The same way we have defined the linear variables in our last chapters before midterm. The rotation variables are angular displacement, angular velocity, and angular acceleration. In this section, we work with these definitions to solve relationship among these variables and use these relationships to analyze rotation motion for the rigid body. We know the rigid body is the body having an equal distance between the 2 points. So, about a fixed axis under a constant angular acceleration. This analysis forms the basis of rotational kinematics. If the angular acceleration is constant, the equations of rotational kinematics simplify, similar to the equation of linear kinematics discussed in the motion along a straight line and the motion in 2 and 3 dimensions. To begin, we know that if the system is rotating under a constant acceleration, then the average angular velocity follows simple relation because the angular velocity is increasing linearly with the time. So, coming with this, the average angular velocity is just half the sum of initial and the final velocity, which has been written here. From the definition of an angular velocity, we find an equation that relates to an angular position, which is omega is equal to delta theta over delta t. Now take this on another side and like that. Uh, Simple and straight. It's like that. Okay. Vf minus Vi. You can write it like that. Like V naught plus omega t is equal to this is the formula. Now where we have set t is equal to 0. Okay. The equation can be very useful if we know the average angular velocity, this one. Then we could find the angular displacement over a given time. Yes, you can find it. Next, we find an equation relating omega, alpha, and t. To determine this equation, we start with the definition of angular acceleration. Now, angular acceleration is here. Now, take it like this and just take an integral on the both sides like that. When you take an integral, you've been ending with alpha t is equal to omega f minus. So we can write it like that, omega f is equal to omega naught plus at, where omega naught is initial angular velocity equation, 10.37 is rotational counterpart to linear kinematics equation. With this equation, we can find an angular velocity of an object at any specified time given the initial velocity and angular acceleration. You need two things, initial angular velocity and angular acceleration in order to find the final velocity. Let's now do a similar treatment with this equation that is of angular velocity. Now take it here. Now take an integral and you've been ending with this equation that is omega f is equal to omega naught, theta naught plus omega naught t plus half at square. Equation 3.8 is rotational counterpart to linear kinematics equation we have found in our last studies before midterm for the position as a function of time. This equation gives us an angular position of the rotating body at any time t given the initial conditions. We can find an equation that is independent of the time by solving equation 10.37 and 10.38. So using this relation, and we've been ending with theta f minus theta naught omega f square minus omega naught square over 2 alpha, and that can be written as that. Now we are going to, that is angular displacement from angular velocity is this. Angular velocity from angular acceleration is this. Angular displacement from angular velocity and angular acceleration is this. And the last but not the least, angular velocity from angular displacement and angular acceleration is omega f square is equal to omega naught square plus 2 alpha delta theta. Now we are going to discuss the exercises related to this problem. This is an exercise 13 from your book, textbook, that is Halliday and Rasnick. The angular speed of an automobile engine is increased uniform from 1170 revolution minute to 2880 revolution minute in 12.6 seconds. Find an angular acceleration in revolution means how many revolutions does the engine make during this time. It's very simple. You just need to apply the difference formula, the delta formula, in order to find an angular acceleration. This is nothing but this. And after finding this, we have to find the revolution. So this is the using of this formula. That is another one that you find the, now simply we've been using this formula as I already told you, putting the values, and we've been ending with 814 revolution per minute. Now, in order to find the angular displacement of an automobile, we've been using this formula: theta is equal to omega initial multiplied by t plus half at square. When we using this formula, we've been getting the initial, we've been getting the angular displacement. Putting the values for this is given in the numerical. This is the time which has been given to us, and this is an angular acceleration that's been already uh, found it, and that is the time. So we've been getting 425.1 revolution. That can be rounded up 425. Now this is the second exercise related to this topic, which is exercise 14 from your fascinating book Halliday and Resnick. As a part of maintenance inspection, the compressor of a jet engine is made to spin according to graph shown in figure. We just need to find the revolutions that the compressor made during the test. This is simply the angular speed on the y-axis and time on the x-axis. When we multiply angular speed multiplied by time, we've been getting the theta, that is actually the displacement, that are the revolutions in our case. So we've been saying this is makes one triangle, the center part forms a rectangle, and this forms an other triangle. So we've been using this and doing our analysis. The upcoming slides show the complete analysis of it. Now this forms the triangle 1, this is a rectangle, and this is the triangle. So this is the first triangle, this is rectangle, and this is triangle. This is the angular speed on the y-axis. When we finding the area under the curve of these three, we've been getting the theta, that is nothing else but the revolution. Now let's do the calculation in the slide. This is area of delta BAA, that is AEBE, plus area of delta CFT, that is the triangle on the right side, FT multiplied by CF, and that is the area of rectangle BCFP, that is BC multiplied by BE, 1 multiplied by 3000, 1 over 2, 5 minus 3 minus 5 minus 3.5, and similarly for the rectangle. And we've been ended with 11, 250 revelation. Now we've been going to discuss the second most important topic of this chapter, that is relation between the linear and angular variables. Consider a particle P in the rigid body, a perpendicular distance r from the axis of rotation. As shown in figure, the particle moves in a radius of the circle. This the angular position of the reference line AP is measured with respect to the x-axis. The particle moves through a distance as along the arc when the body rotates through an angle, such as. Now this is a relation which we're getting from the figure. We have already studied this relations in our rotation variables slides. S is equal to r theta, where S is in the radian. Differentiating both sides, we've been ending with V is equal to omega r. We have already proved this thing in our preceding slides. This is the relation between the magnitude of tangential linear velocity, which can be written as Vt or 2, where t represents the tangent, and then angular velocity. The linear speed of the particle in the circular motion is the product of the angular speed and the distance r of the particle from axis of rotation. Differentiating both sides, dv over dt is equal to d omega over dt multiplied by r. However, dt is a magnitude of tangential component at of an acceleration of the particle. D omega t is the magnitude of an angular acceleration of rotating body, so we can write it like that. That is the relation of angular acceleration and the linear acceleration. Hence, the magnitude of the tangential components of linear acceleration of a particle in circular motion is the product of the magnitude of angular acceleration and distance r of the particle from axis of rotation. Radius or the centimeter component AR of the acceleration is Vt square over R of a particle, that is AT Vt square over R is equal to omega R square. All above equations enable us to prescribe the motion of one point on a rigid body about fixed axis either in angular variables or in linear variables. Now we are going to discuss the problem related to this topic. First, it is the problem from your textbook, that is Halliday Resnick problem number 6. An astronaut is being tested in centrifuge. The centrifuge has a radius of 10.4 meter and in starting rotates according to this. Again, this is the displacement as the acceleration is multiplied with the time scale. When t is equal to 5.6, what are the astronaut angular speeds? Simple and straight. You've been taking this derivative and this is this and put t is equal to 5.6. For the parts b, that is tangential speed, simply you need to use the relation which we have find just from this. You're going to this and use the radius and simply you've been getting the tangential speed and tangential acceleration, nothing but the derivative of this and using the similar r and the radial acceleration. So let's discuss. First of all, the angular speed of an asteroid can be found by this formula. Putting this using this differential property. Now we've been ending with this relation. For time value, that is 5.6 seconds, we've been ended with 3.65 radian. That is an angular speed of astronaut. Now the tangential speed, that is v is equal to r omega, as I wrote in our last slide. So just put this 10.4 second and omega value which we just found. So we've been getting 38 meter per second square. To calculate the tangential acceleration, we have to find an angular acceleration first, as I already told you. Let's find it, no problem at all. and the tangential acceleration of astronaut is alpha t is equal to alpha r. So just take this and again using the same property of definition which we have already studied in our rudimentary classes. So just take this, we've been ending with 0.652 radian per second. Use this in our this relation. We our answer that is 6.78 meter per second. Last part that is very interesting, that is radial acceleration of an astronaut. Now this is our relation. Just use omega for it and multiply by with the radius that is 138.85 meter per second. Now this we are going to discuss the second problem related to this topic. This is an exercise number 33 from your textbook, Alidin Resnick. A rigid body rotating about the z-axis is slowing down at acceleration of 2.66 radian over second square. Consider a particle located at distance r that is a position vector in j and with the j unit vector and the k unit vector. So we can say it's lying in y and z axis. Okay, at an instant of that, that is an angular velocity. Find the velocity of the particle is acceleration and what is the radius of the circle. Now we are going to find the linear velocity of the object. We can find this by a very simple formula v is equal to omega r square. We just have to put the values given in our numerical and that is omega 14.3 with the unit vector k and the position vector having unit vector j and the k. We know from our basic rudimentary classes that the k cross k would be equal to the 0 and we've been getting the cross product k multiplied by j in the direction of I unit vector. It means that it's along an x-axis. Simply multiply these two and we've been getting 26.1 and this minus is coming from the direction of unit vector. Now moving towards the second, we will have to find an acceleration, angular one. So we've been just using the values we have. So first of all, we've been using this formula and we've been putting the values in it. First of all, 2.66 multiplied by unit vector multiplied by the velocity and then angular velocity. Whereby by using this is two component. One is tangential component of an angular acceleration and other is the radial component. On using this formula, we've been ended with 4.87 meter per second square with a unit vector I and the other minus 373.2 meter per second square with a unit vector j. Now we have to find an angle vector for horizontal and corresponding position vector. Just as we know tan inverse y r of y over r of an x, we've been given that value 13.45. It is important to note that angle corresponds to the position vector of an object in the YZ plane. Okay, so as shown in the figure, and this has been clearly illustrated here. So this is the theta is equal to 34.5. Now we want to find this angle, so simply using the trigonometry rule from our basic rudimentary classes, 90 minus 34.5, we've been getting something around 55.5. This is the angle suspended by the projectile or the vertical angle that is 50.5, which I've been discussing in the last slide. So it can be seen from the above figure that the radius of the curvature of the particle can be found by this formula by using the figure, and r is equal to r sine of theta. Okay. And r is the magnitude of the position vector of an object. We can simply find the magnitude of anything by squaring it. There is square here. So by using it, we've been getting 22.22 meter per second. And after putting that value into the previous equation, we've been getting 1.82 meter. Therefore, the radius of the curvature of the object is 1.82 meters. Thank you for your time. That's I have for you related to chapter 8. Now we've been going to discuss chapter number 9, which is related to rotational dynamics in our upcoming lectures. Stay blessed. Allah Hafiz.